Hey there. This is a video to go over the review problems, the circular motion and gravity practice problems given to AP Physics students. I apologize for any sniffling, hoarseness in my voice. We'll just try to get through these as painlessly as possible. I'll be reading the questions and going over the kind of thinking that will lead you to the problem-solving strategy and ultimately the correct answer. Starting with this one, on the 2001 AP Physics B exam, a ball of mass m is attached to a string of length r and negligible mass. The ball moves clockwise in a vertical circle shown above. When the ball is at point P, the string is horizontal. Point Q is at the bottom of the circle and point Z is at the top of the circle. Air resistance is negligible. Express all algebraic answers in terms of the given quantities and the fundamental constants. So what that means is any expressions that they ask for will involve given quantities such as this m, then this r, also listed here. Part A, on the figures below, draw and label all forces exerted on the ball when it is at points P, Q, respectively. So I'm going to use this drawing pad here to kind of copy those circles. So we have the circle. Oh, that's not very good. Okay, so here are points P and Q, and the question asks to draw and label all the forces exerted on the ball, where these black spots are the ball. And it's a vertical circle, so we can assume that gravity is acting on the ball during both instances. So I'm going to label the forces in, let's use blue. So gravity will always act downward on the ball. And the length at which I'm drawing these force vectors should be the same since the mass isn't changing, and force of gravity is only dependent on the mass of the object and the mass of the Earth and how far away they are from the center, how far away apart they are. The other forces acting on the ball is this force of tension that's causing it to go in a circle, and then this force of tension, where this is the center. So these force vectors should be drawn at right angles to each other. And then these force vectors, since Q is directly at the bottom, the tension in the string is pulling it directly upward, so these are should be in line. Part B asks to derive an expression for the minimum speed the ball can have at point Z. Remember, point Z is at the top of the circle, without leaving the circular path. So this is saying that what's the minimum speed that it can have where it's still going to come back down and follow that circular path. And if we're looking for a minimum speed, then we want the minimum amount of forces acting on that ball. So we can say that for that short moment that it's at the top of the circle, the only force acting on it is gravity. So if we have a picture like this. So this is point C, and gravity is the only force acting on it, downward. Label that force of gravity. And we still want it to stay in a circle. So the source of centripetal force is just going to be that force of gravity. In this case, since we are on Earth, we're just using the weight. It's going in circles, so we can assume there's centripetal acceleration, and we have an equation for that. mv squared over r, is equal to the force of gravity, which is mass times g, where g is 9.8 meters per second squared. We want to just solve for the velocity that this ball is going to have if the case is that gravity is the only thing causing it to go in a circle. That's the story this equation is telling us. Then just using algebra, we can cancel this out. So the m, we could move this around to solve for v. So the m here, we got to ask ourselves, what is this m? It's the m that of the object that's moving in a circle, and in this case it's the ball. And the m here is the mass of the object that gravity is acting on, also the ball. So these are the same m's. They can cancel out. If I want to solve for v, I want to isolate v. First thing I probably have to do is multiply both sides by r, so I could get rid of this r. And then take the square root of both sides to give me that v. And that's how we get the final answer. Part C asks the maximum tension the string can have without breaking is T max. Derive an expression for the maximum velocity the ball can have at point Q without breaking the string. So point Q is going to be this bottom point here. So now the case is that gravity isn't the only thing causing it to go in a circle. Since at this point there's going to be more than one force acting on it, we can take the sum of those forces Newton's second law. They will equal the mass of the ball times its acceleration. And now the forces, you have this maximum tension and the force of gravity. Now if I set up to be positive, then the magnitude of this tension force is also positive. And whatever I get for the magnitude of gravity, if I'm just using positive 9.8, I could set this to be negative. And this thing is moving in a circle, so we can say that its acceleration is centripetal. And so on the other side of this equation, we have the centripetal force. So the things that are causing it to go in a circle can be listed on this side as the sum of forces. Remember, centripetal force is just a net force. We don't put centripetal force as one of the forces that we sum up. It's a result of all these forces. It's the resultant force of tension force and gravity or weight. So this T max is just a given variable. We can list that out just like that. And we still have mg, but maybe now I want to write in this mv squared over r for centripetal force. I'm substituting the formula for centripetal force. And we want to solve for the velocity, so I have my expression now, and all that's left to do is solve for v. And with a little bit of algebra, if I move this m and r over to the side, so first moving the r over, I'm going to put this in parentheses. That's an r. Oops. So then we just have mv squared, and then divide both sides by m. We're left with v squared is equal to all of this. Over m, and then finally taking the square root will give us the final answer. So that is the maximum velocity that the ball can have, given that it's pushed the limit of the string has been pushed to its max, the tension in the string. Part D asks, suppose that the string breaks at the instant the ball is at point P. Describe the motion of the ball immediately after the string breaks. So let's move this. At point P, the ball is on its way upward, and we can say that at point P it's tangential velocity. And tangential velocity, the term just comes from knowing that the the vector for velocity is tangent to the circle that it's making with its path. So its tangential velocity at this point can be represented with this green vector as just like that. And at this point, when it's attached to the string, it has tension applying a force to the ball that's causing it to go this way. If it weren't for that tension force, its velocity would stay the same. Acceleration is a change in velocity, and forces cause things to accelerate. We know that from Newton's second law, F equals ma. If there's no force, there's no acceleration. If there's no net force, there's no acceleration. So the net force, being the centripetal force in this case, breaks off. So now you don't have tension, although there is one other force still acting on it, and that's the force of gravity. So its tangential velocity will, at this point, point upward. So it will continue to move upward. However, because there's weight acting on it, there's this force of gravity, it's going to slow down. So it's going to go straight up, and then due to that net force due to gravity, it's going to accelerate downward. So next one, so now we're on page 2 of the review sheet. A car rounds a curve at constant speed. If the car's speed doubles, the net force on the car will multiply by a factor of one of these. So the force is going to change. Let's see where we can imagine that happening mathematically. If the car is going in a circle, we can assume that there's a net force acting on the car, causing its acceleration to point inward towards the center of that circle. And we say that that's centripetal acceleration. I'm going to refresh the page here. So that centripetal force has a formula. This F, So if the mass of the car doesn't change, and the distance that the car is from the center of the circle, that's what this r is. Don't be confused. Just because it's r doesn't mean it's always a radius of a circle. You want to think of this r as the distance between the object that the force is acting on and the center of its motion. If those things don't change, but this is doubled, so instead of v, now it's, so this new force, let's just call it Fc prime, this velocity is now doubled. What result is that going to have on the force as a whole? Well, anytime we change velocity, we're actually changing it by this square amount. So any factor that it gets changed by, ultimately the whole equation on this side is going to be changed by that factor squared. So if velocity is doubled, then we can say that the final force is going to be 4 times the amount that it originally was, because this is the amount that it originally was. We choose a different color to highlight that. This is just the same thing as this. So this new force, this new centripetal force, is 4 times the original one. And so the correct answer, go back to here, is the net force changes by a factor of 4. The next one, I think this is number 3. A planet of mass m orbits around the sun in a circle. The speed of the planet in its orbit is v. The distance from the planet to the sun is d. And the magnitude and direction of the net force experienced by the planet, what is it? So they're giving us variables, so we need to come up with an algebraic expression that uses those variables. What they're telling us is that something's moving in a circle. Something's moving in a circle, that means the net force acting on it, we can say is a centripetal force. And because it's an